Welcome to a new episode.
Hello and welcome back to the Copper Connection podcast with me as always your host Chris Bailey. Over the last 3 weeks we kicked off our level 2 plumbing revision mini-series designed to help you tighten up your knowledge, boost your confidence and walk into that exam fully prepared. I'm really glad you're with us here today because today's episode is a big one. We're covering hot water systems and I want to tell you right now this unit is one of the most important in your entire level 2 qualification. It comes up heavily in the exam, it's directly relevant to your day-to-day work on the tools, and once you understand it properly, it all makes complete sense. Hot water is something every single person in the UK uses every day, but as a plumber, you're not just turning on the tap, you're responsible for making sure that water is stored safely, delivered at the right temperature, and the system protecting it from overheating or overpressurising is working correctly. Get it wrong and people get hurt. Get it right and you're a professional who can be trusted. So today we're going to follow the journey of hot water from the moment cold water enters the system all the way to the moment it flows out the tap or shower head. Along the way I'll walk you through every key topic, every regulation, every calculation and every common mistake that students make in their exams. I'll be flagging things clearly so when you hear key fact that's something that you must be able to recall. When you hear exam tip, that's something examiners love to test. And when you hear common mistake, that's the traps to avoid. And when we hit calculations, I'll walk you through them step by step. So grab a pen, get comfortable, and let's get into this week's episode. Before we even think about pipework, cylinders or thermostats, we need to talk about the rules. Because in plumbing, everything you do is governed by legislation and industry standard. The exam will test whether you know which key documents applies to which situation. So let's nail this down now. Let's start with Building Regulation Approved Document G. This is a big one for hot water. If you can remember nothing else from this section, remember this. Approved Document G is the key building regulation for hot water temperature and safety. It's split into parts and part G3 is specifically about hot water. Let me walk through what G3 actually says, because each part could appear as an exam question. So we've got G3 Part 1, says the hot water must be supplied to a basin or adjacent WC and to any food preparation area. Think about it, hygiene, you need hot water near toilets and kitchens. G3 Part 2 says that hot water systems must be able to resist the effects of temperature and pressure during the normal use. In other words, the system must be built to handle what it's designed to do. G3 Part 3 says that hot water must never reach 100 degrees C. If there is any discharge from the system, for example, the safety valve, it must be visible by a ton dish and safely conveyed away. This is why ton dishes and discharge pipework on unvented systems are critical. G3 Part 4 says that in new builds and conversions, the water temperature to a bath must not exceed 48 degrees C. This is scalding prevention measure, particularly important for protecting children and vulnerable people. Exam tip, if a question asks you a approved document relates to hot water temperatures, the answer is always going to be G. If it asks about energy efficiency and installation, the answer is going to be L. These two are commonly confused. So let's talk about approved document L, which is about energy efficiency. Document L is about conservation of fuel and power. It requires that hot water systems are properly insulated, the cylinder, the pipework and the building fabric. It also requires that systems are controlled using programmers, thermostats and oil valves. The goal here is to reduce CO2 emissions and energy waste. Key fact, heat recovery time. This is the time it takes to heat a cylinder from cold. Should be around 20 to 25 minutes. This is linked to the building regulations part L. Now let's take a look at the water supply water fittings regulation 1999. These regulations are incredibly detailed and come up regular in exams. So let me go through the key points one by one. Hot water must be stored at 60 degrees C and distributed at 55 degrees C. At any outlet, 50 degrees must be reached within 30 seconds of the tap opening. The regulation also deals with dead legs, sections of pipework where water sits stagnant and can become a Legionella risk. Keep back dead leg limits. So on a 15mm pipe, dead legs cannot be any longer than 12 metres. And on 22mm pipe, can't be longer than 8 metres. A common mistake made here is students often get it the wrong way round. Remember, the smaller pipe, 15mm, is allowed to be longer, 12 metres. The larger pipe, 22mm, must be shorter, 8 metres. Think about it. A larger pipe holds more stagnant water, so it needs to be shorter to reduce that risk. The regulation also states that 4% expansion must be accommodated in the system, either by the system or an expansion vessel. The open vent must have a minimum diameter of 19mm, hence why we always say 22mm, and it must vent over the cold water storage system. Other key standards you might also know about the BS-EN 806, parts 1 to 5, and BS 8558. Both cover the design, installation, testing, and maintenance of hot water systems. Think of the British Standard 855A as the companion document to British Standard EN 806. They work together. The gas safety installation and use regulations requires that anyone working on gas appliances must be gas registered. This is a legal requirement, not optional. And the IET 18th edition wiring regulations, BS 7671, cover all electrical work, including immersion heaters, pumps, and shower units. Exam tip: when commissioning an appliance and flow rates and pressure, always refer to the manufacturer's instructions. They override general guidance and are specific to that appliance. Okay, so now let's get into what to consider when designing a system. Now, imagine you've been asked to design a hot water system for a property. Where do you start? The exam loves questions about system selection, so let's think about this logically. First of all, we've got to think about the occupancy. The number of people living in a property directly affect the size of everything. More people means more demand for hot water, which means a larger cylinder, a larger cold water storage system, and larger distribution pipework. A family of 5 with 2 bathrooms needs a very different system to a single person in a studio flat. We also have to consider type and size of the building. Where is the boiler? Where is the cylinder? How far is the hot water travelling to reach the outlets? Longer pipe runs create dead legs and heat loss. In larger buildings, secondary circulations may be needed to keep the hot water moving around the system, so it's always available quickly at the tap. Also, we've got to consider available services. Is there gas? Is there adequate electrical supply? What size is the incoming main? These all affect which system is appropriate for that situation. Let's have a look at a couple of typical pipe sizes that you need to know. So, as we've already mentioned, the open vent pipe is a minimum pipe size of 19mm. Cold feed to a cylinder is a minimum of 22mm, but it must equal or exceed the hot distribution pipe. Hot distribution, 22mm. Cold mains for unvented system, 22mm. Hot feed to taps, generally 15mm. Hot feed to bath, 22mm. And hot feed to shower, 22mm within 1 metre, and then reduces to 15mm. Key fact: the most common hot water cylinder is 450mm diameter and 900mm tall. Exam tip: the cold water feed must always equal to or larger than the hot distribution pipe. You can't have a cold feed that is smaller than a hot pipe it's feeding. So let's have a look at types of hot water systems. This is where the exam really tests your understanding. You need to know the difference between centralised and localised systems, between direct and indirect, between storage and instantaneous. So let's break them down clearly. We've got centralised versus localised. Centralised: one central heat source delivers hot water to multiple outlets throughout the property. Localised: the heater is at or very near the point of use. So a combination boiler is a centralised system. A single point water heater under the sink is localised. A large open vented cylinder in an airing cupboard is centralised. And an electric shower is localised. So let's have a look at storage versus instantaneous. Storage: well, water is heated and stored in a cylinder ready for use. Instantaneous: well, water is heated on demand as it flows through the appliance. A hot water cylinder is storage, a combination boiler is instantaneous, a thermal store is instantaneous, and a single point heater is instantaneous. So, direct hot water systems. Let's start following the water. In a direct system, cold water enters from the cistern, drops into the cylinder, and is heated directly by either a boiler or an immersion heater. There is no coil. The water that gets heated is the same water that comes out of the tap. Key fact: in a direct system, primary water and domestic hot water are the same. There is no separation. Then we have boiler heated direct system. This is an old system, largely replaced now. The boiler circulates water directly through the cylinder. Because the same water goes through the boiler, it can become dirty over time, picking up debris and scale from the boiler. It's a low pressure system fed from a cold water storage system. And then we have immersion heated direct system. This is the modern version of a direct system. It's used where there is no boiler, perhaps in a flat with electrical heating only. An immersion heater is an electrical element that sits inside the cylinder and heats the water directly. Many cylinders now have two immersion heaters, one at the bottom to heat the full cylinder and one at the top for a quick boost. This gives flexibility and a backup heat source. A common mistake is students sometimes think direct means high pressure. It doesn't in hot water. A direct fed from a cold water storage system is a low pressure system. Only unvented systems are classified as high pressure. Now we move to indirect systems, and this is where the exam really digs in. You need to understand the principle clearly. Key fact: in an indirect system, the boiler heats primary water. That primary water flows through a coil, heat exchanger inside a cylinder. The coil heats the domestic hot water, but the two waters never mix. Think of it like this. Imagine a coiled copper pipe sitting inside a tank of cold water. You pump hot water through the coil, the heat transfers through the copper walls into the surrounding water. The hot water in the coil and the cold water in the tank never touch, but heat passes between them. That's exactly how indirect cylinders work. Open vented double feed indirect system. This is the most commonly traditional indirect system. It has two separate feeds. The first feed comes from a cold water storage system and supplies the base of the hot water cylinder. This is the cold feed for your domestic hot water. The second feed comes from a separate smaller system called the feed and expansion system. This supplies the primary circuit, the boiler and the coil. The system also has an open vent pipe. This is your safety pipe that rises up from the primary circuit and terminates over the cold water storage system. It allows expansion and prevents pressure buildup. There's a calculation to remember here. So open vent heights. The open vent must rise a minimum height above the water level in the system. So the formula is vent height equals 150 millimeters plus 40 millimeters per height in meters. So if the system height is 3 meters, it'd be 150 millimeters plus 40 millimeters times 3, so that's 120. So it'd be 150 plus the 120, which would give us 270 millimeters. So the vent pipe rise must be at least 270 millimeters above the water level in the system. Common mistake here: students forget to add the base 150 millimeters before multiplying. Always start with a 150, then add 40 per meter of height. Next, we have an open vented single feed prismatic system. This is an old system that is no longer installed. It's still used a single feed from the cold water storage system to supply both the primary and secondary circuits. The primary and secondary circuit water are kept separate by an air bubble lock inside a specifically designed cylinder. The problem here: if the air bubble is lost to excessive expansion, the two waters mix. The domestic hot water becomes contaminated with the boiler water. This is why it's no longer used. Exam tip: if asked to upgrade to a prismatic system, to a modern low-pressure indirect system, using the existing boiler, install an open vent double feed indirect cylinder. Open vented combination units or voltaic cylinders. This is your all-in-one unit where the cold water system sits directly on top of the hot water cylinder. Because this system is so close to the cylinder, the head height, the vertical distance between the water surface and the outlet is very small. This means the system operates at very, very low pressure. Key fact, combination units or voltaic cylinders are used in flats, holiday cabins, where space is limited and low pressure is acceptable. Common mistake, do not confuse a combination unit with a combination boiler. A combination unit is a cylinder with a system on top. A combination boiler is an instantaneous gas appliance with no cylinder at all. They're completely different things. Then we have our thermal store. Works in the opposite way to a standard indirect cylinder. Instead of storing domestic hot water and heating it via a coil, the thermal store stores hot primary water, the boiler water, and uses a heat exchanger to heat cold mains water on demand as it flows through. Key fact, in thermal store, the primary water fills the cylinder. Cold mains pass through the heat exchanger coil and is heated instantaneously. It is an instantaneous system. Okay, so now let's take a look at instantaneous and localized heaters. Let's start with a single point water heater. A single point heater serves one appliance only, typically a sink or a basin. It's a localized system. The heater is usually rated between 8 and 11 kilowatts. Key fact, a single point heater is inlet controlled. The tap allows the cold water into the unit, which pushes the hot water through the spout. The spout itself acts as an open vent. You may notice it drips slightly as the water inside expands when heated. On undersink versions, a vented tap must be installed to act as an open vent. Then we have multi-point water heaters. A multi-point water heater serves several appliances locally. For example, a kitchen, a nearby bathroom. Unlike the single-point heater, it is outlet controlled. You open the tap, the flow of water activates the heater. So a good exam tip here, this often comes up in exams. Remember, single point equals inlet controlled and multi-point equals outlet controlled. If asked what heater to install for a remote kitchen sink in a community hall, suggest a multi-point heater. And then we've got the combination boiler. The combination boiler is a centralized instantaneous system where you open the hot tap, the boiler fires up through a plate heat exchanger. There is no stored water, it's all on demand. Don't forget, combination boilers have hot water priority. The boiler can heat either the central heating or the domestic hot water, but not both at the same time. When you open the hot tap, the central heating pauses until that tap is closed. Exam tip, for a small 2-bedroom property with 1 bedroom and limited space, a combination boiler is an ideal choice. No space needed for cylinder, cistern, compact, and it's efficient. Now let's turn our focus onto showers, the different types and installation. Showers come up regularly in exam. The diagrams can catch students out. Let's go through each type clearly. We'll start off with a gravity mixer shower. This shower is fed by gravity from both the cold water storage cistern and the hot water cylinder. No pump is needed. The hot and cold water are blended at the mixer valve before reaching the shower head. Key fact, a gravity mixer shower requires a minimum head of 1 metre between the bottom of the cold water storage cistern and the shower head. The safest type of mixer valve is the thermostatic mixing valve. This reacts to changes in incoming water temperature and pressure, maintaining a safe, constant outlet temperature. Then we have boost mixer showers. When the head height is insufficient, a pump is added to boost the flow. There are 2 different types. We have a double impeller pump. A double impeller pump has 2 separate impellers, one for hot and one for cold. It draws the hot and cold water separately from the cylinder and the cistern and pushes them individually towards the mixer valve where they are blended. The pump is positioned before the mixer valve. A single impeller pump has 1 impeller. The hot and cold water are blended at the mixer valve first, and then the single impeller draws the blended water and pushes into the shower head. The pump is positioned after the mixer valve. In exam diagrams, look at the pump symbol, a circle with a black triangle. If the pump is before the mixer valve, it's a double impeller. If it's after the mixer valve, it's a single impeller. Then we have our tried and tested electric instantaneous showers. This shower is fed directly from the cold mains. It heats water on demand using an electrical element. Typical ratings are between 8 to 11 kilowatts. Key facts: if a property only has a cold main supply available, for example in a new ensuite, install an electric instantaneous shower. It requires no hot water supply at all. And a common mistake: electrical showers must be wired by a competent electrician. Never attempt electrical work unless you are qualified and authorised to do so. Now let's take a look at temperature control and system safety. This section is absolutely critical. Hot water safety is not just about comfort, it's about preventing scalding, preventing Legionella, and preventing catastrophic system failures. The exam tests this heavily. So we'll start with our cylinder thermostat. The cylinder thermostat is strapped to the outside of the cylinder, positioned 1/3 of the way up from the base. It monitors the water temperature and cuts the heat source when the set temperature is reached. The cylinder thermostat is set at 60 degrees. It is positioned 1/3 up the cylinder. Why 60 degrees? Well, below 50 degrees, Legionella bacteria can survive and multiply, and above 65 degrees, limescale begins to form in hard water areas. So 60 degrees is a safe middle ground, hot enough to kill bacteria, cool enough to prevent scale. Common mistake: students sometimes say the cylinder needs to be set at 50 or 65. It's 60 degrees and is positioned 1/3 up the base, not at the top. Then we have our boiler thermostat, located on the boiler itself. This sets the temperature of the primary flow and return water. The maximum temperature allowed for this is 85 degrees C. Then we have our overheating thermostat. This is a safety backup. If the boiler thermostat fails and the water temperature begins to rise above 85 degrees C, the overheat thermostat puts the boiler into lockout, cutting the power and stopping the system. On an unvented system, it also closes its own valves. So, unvented system, the 3 tiers of safety. Unvented systems are sealed and pressurised. They're connected directly to the mains because there is no open vent to relieve pressure. And they have 3 layers of safety protection built in. So tier 1, first line of defence, is a cylinder thermostat, usually set at 60 degrees. This is your normal operation. Second tier is your overheat thermostat, which we set at 85 degrees C, cuts power if cylinder stat fails. Temperature. Third is temperature and pressure relief valve, TPRV, which is set at 95 degrees C or 5 bar. This is your last resort of your safety device. Key fact that the temperature and pressure relief valve is located at the top of the unvented cylinder. It is the last line of defence. If both thermostats fail, it opens and empties the cylinder. All the discharge goes through the ton dish and is safely conveyed away. A common mistake: do not confuse the pressure relief valve, that usually opens around 3 bar, usually due to expansion vessel failure, with the temperature and pressure relief valve, which opens at 95 degrees or 5 bar as a last resort. They are different devices with different functions. Okay, so now let's take a look at thermostatic mixing valves, TMVs. A thermostatic mixing valve blends hot and cold water to deliver a safe, consistent temperature at the outlet. They are used to prevent scalding, particularly important for vulnerable people, such as children, the elderly, and those in a care setting. Then we have 2 different types of TMVs. We have TMV2, which is used in domestic properties, and TMV3, which is used in healthcare settings, like hospitals and care homes. The maximum pipe length after a single TMV installation is 2 metres. Beyond that, the water may cool down too much before reaching the outlet. So let's have a look at some of the TMV temperatures that you need to know, because you could be tested on these. So we have a bath in a domestic setting. The temperature should be 41 to 44 degrees. Shower in a domestic setting should be 43 degrees, but then a shower in a care home is slightly less at 41 degrees. A basin is 43 degrees, a bidet is 38 degrees C, a Kitchen sink is slightly higher at 46 to 48. And group showers and basins, so the ones you see in gyms or swimming pools, are between 38 and 40 degrees, but must not exceed 43 degrees. Good exam tip here, the kitchen sink is set higher, 46 to 48, because it needs to kill bacteria and cut through grease. However, this does create a scalding risk, which is why it's important to be aware of the context when setting TMV temperatures. And a common mistake, students often confuse bath temperatures of 41 to 44 with shower temperatures, 43. Remember, the bath is slightly lower because people immerse their whole body, increasing the risk of scalding. In a group mixing insulation, for example, a row of wash basins in a school, one TMV serves multiple outlets. In this case, you must be careful about Legionella risk due to longer pipe runs, and regular disinfecting may be required. Okay, so let's have a look at commissioning and testing. Once a hot water system is installed, it must be tested before it's handed over to the customer. This is not optional, this is a legal and professional requirement. First of all, we'll have our visual inspection. Before any pressure tests, carry out a thorough visual inspection. Check all joints, fittings and valves and connections. Make sure everything is connected and installed and there is no obvious issues. Exam tip, the correct sequence is visual inspection, soundness test, flush system. This comes up in exams, don't get this in the wrong order. Okay, so once we've finished, we will fill our system up, and once we add water into our system, we leave that for 30 minutes. This is what we call stabilisation. Then we would add our pressure into the system. For rigid or copper pipe, or metallic pipe, this would be 1.5 times working pressure. So if you've got 3 bar coming in, 1.5 bar, 3 times 1.5, and that's what we're testing to. We add the pressure on and we'll leave that to 60 minutes. Once we check after 60 minutes, if there's no pressure loss whatsoever, this is classed as a successful pressure test. If there is a loss, you need to go and have a look what needs rectifying and then retesting. Don't forget, we have 2 pressure test types. We have type A and type B. So type A is for rigid pipe, which I've spoken about. And then we have pipe work for test B, which is plastic pipes, where we fill the system up and pressurise at working pressure. We leave for 30 minutes, check the pressure, leave for a further 30 minutes to check the pressure again, and the pressure loss is less than 0.6 bar with no visual leaks, as classified as a success. So again, once you come in to pressure test your commission, if you've used the majority in copper and a bit of plastic, always do the copper. You know, you've got to look at what you're using. A common mistake for the soundness test for plastic pipe is not carried out at 1.5 times working pressure. That's for copper. Test B for plastics uses working pressure, so you need to understand the 2 different tests. So after we've done our pressure test or soundness test, once the system passes the soundness test, you must flush through with cold water to remove any debris and flux residues from the pipework. Then refill the system, carry out the following checks. Inspect water levels in systems. Check that all valves are holding correctly. Flow operated valves, taps and drain offs. Check flow rates and outlets using a flow cup or a weir cup. Check pressures using a pressure gauge. Check temperatures using a thermostat. All of these must meet the manufacturer's specifications. And finally, complete the benchmark certificate. This is an official commissioning document that proves the system has been installed and tested correctly. And then there's decommissioning. Decommissioning means taking a system out of service. There's 2 types. We have temporary or permanent. So temporary decommissioning, this is carried out when servicing or replacing a component. The system will be reinstated after a short period. You must advise the customer before starting, and some of the steps would include isolate the mains water supply, carry out safe electrical isolation if needed, drain the system or the relevant part of it, complete the work and then reinstate and recommissioning. Key fact to prevent the water being turned back on accidentally during temporary decommissioning: label the valve do not use and inform people in the property the water will be switched off. And then we have permanent decommissioning. This is carried out when the entire system is being removed and will not be reinstated. Steps will include isolate the mains water supply, carry out safe isolation, electrical isolation, drain the system safely, cap off the incoming mains and label it, remove the electrical supply from the fuse spur safely, remove all component parts. Safe electrical isolation is covered in a different unit. Make sure you revise it. Exam questions about replacing electrical components like showers and pumps will expect you to know the correct isolation procedure. Okay, so that brings us to the end of this week's episode, where we have looked at hot water systems from start to finish. We've followed cold water all the way through, from incoming supply through the storage and heating, through safety controls and temperature management, all the way to the outlet. We've covered the regulations, the system types, the calculations, the commissioning processes and the decommissioning step. I want you to take a moment to recognise how much you just covered. This is not simple stuff. This is professional level knowledge that real plumbers use every single day on real jobs, and you're learning it. Here's what I want you to do after this episode. Go back through your notes and write down 3 things you found hardest to remember. Then focus your next revision session just on them 3 things. Don't try and revise everything at once. Target your weak spots. Remember the key numbers: 60 degrees for cylinder starts, 85 degrees for overheats, 95 degrees for the TMVs, 19mm minimum for an open vent pipe, 0.6 bar soundness test for plastic pipe, and 20 to 25 minutes for heat recovery in a cylinder. These numbers will come up, these numbers will hopefully come up in your exam. And remember, you're not just studying for an exam, you're building the knowledge that will keep people safe in their homes. That matters, you matter. You've got this, keep going, keep revising, and I will see you on the next episode of the Complicated Podcast.
We'll be back next week. In the meantime, please subscribe and thanks for listening.